Hi everyone, today we are going to go over circular motion and what is covered in AP Physics on circular motion. So the first thing that we're going to look at is what is uniform circular motion, and you actually just watched a video on this, so we're going to go through this pretty quickly. But an object that's moving at uniform speed in a circle with a constant radius is said to have uniform circular motion. So why is uniform circular motion considered accelerated motion? Well, what does acceleration mean? Acceleration means change in velocity. And what is velocity? Well, velocity is a vector. So since velocity is a vector, then if velocity is changing direction, then you're going to have accelerated motion because you're going to have a change in velocity. So even though the speed is going to be constant, the velocity is not constant since it's moving in circular motion and it's changing its direction. So oftentimes we hear about a thing called centrifugal force. What is centrifugal force? So centrifugal, center fleeing force is what everyone thinks. So centrifugal force is the force that flings an object in circular motion, right? Well, that's actually not right because as you learned in your last video, centrifugal force is a myth. There is no outward directed force in circular motion. And the reason for that is because of Newton's first law. So what is Newton's first law? Newton's first law is an object in motion is going to stay in motion unless acted on by an outside force. An object at rest is going to stay at rest unless acted on by an outside force. So in motion will stay in motion, and at rest will stay at rest. Okay. And so what happens is, say you're in your car and you're flinging in your car. Well, the reason that you feel yourself being pushed is because your object is resisting, your object being your body is resisting that change in motion, that change in velocity. So Newton's first law in cars, to explain that a little bit more, when a car accelerates forward suddenly, you as the passenger are going to feel like you're flung backwards, correct? So you are not actually being flung backwards, and you know that. Your body is initially at rest. And so what ends up happening is when the car accelerates, your body is resisting that change in motion. So when the car brakes, suddenly you kind of feel like you're flung forward. And the reason that you feel like you're flung forward is because your body is moving at a velocity forward. And so when the acceleration works against you, or when the force works against you, what ends up happening is you feel like you're flung forward because your body is resisting that change in motion. So now let's look at it in terms of circular motion. When we're going in circular motion, you feel as if you are flung to the outside. A perfect example is, say someone is turning right, you're turning right at a light and you take that right really like a wide right turn. And so your body is all of a sudden going to feel like it's being flung to the outside. And the reason for that is because of centripetal force. You're not actually being flung to the outside. Your inertia is going to resist that change in motion, that inward acceleration. And so your body wants to keep going straight. That's why you feel that turn, that fling. The force on your body and the resulting acceleration actually point inward. And that's going to be the most important concept when we're looking at centripetal acceleration and centripetal force. Now remember, force and acceleration, or net force and acceleration, are in the same direction. Net force and acceleration are in the same direction. So centripetal, what is centripetal? Centripetal is center seeking. That type of acceleration, centripetal or center seeking acceleration, points towards the center of the circle and is going to keep the object moving in circular motion. This type of acceleration is at right angles to the velocity, okay? This type of acceleration does not speed up the object or slow it down, meaning your speed is not changing, it's your velocity that's changing. So as you're moving around in circular motion, okay, your velocity is going this way, but your acceleration is going this way. And so your acceleration is actually going to be more towards that center because it's going to go to the center point of your circle, and this is going to be a 90-degree angle. So your velocity is constantly being forced to move because there's an acceleration or a force acting against it towards the center of the circle. So when we look at another image, we have our 90-degree angle here, okay? This is called our tangential velocity. Our centripetal acceleration is equal to v squared divided by r. V squared divided by r, where AC is our centripetal acceleration. V is our tangential speed in meters per second, and r is going to be our radius of our circular motion. It is very important for you to recognize that it always points towards the center of the circle. This is a major concept in AP Physics. You are expected to know that when you have any kind of circular motion, you have your net force or your acceleration is directed towards the center of the circle. So when you're looking at centripetal force, well, we know that force is going to be your mass times acceleration. The net force responsible for centripetal acceleration is called your centripetal force. So let's see, we know that sum of forces is equal to mass times acceleration. Centripetal force is simply mass times centripetal acceleration. So go ahead and use some substitution here, and you end up getting mv squared divided by r. So our sum of forces when we're dealing with centripetal motion is mv squared divided by r. Now, any force can be your centripetal force, okay? And it always has an identity. We don't ever actually call the identity of the force the centripetal force because centripetal force is really a sum of forces. Centripetal force is a sum of forces, okay? So this can be applied to any different situation that's going to cause an object to move in a circle. And you can identify the real force or the combination of forces which are causing that centripetal acceleration. Any force can act as centripetal force. So for example, as I have a car, as a car makes a turn on a flat road, what is the real identity of the centripetal force? Static friction, because it's friction that's actually holding the tires on the road. Let's try this one. As a weight is tied to a string and spun in a circle, what is the real identity of the centripetal force? What is causing that circular motion right there? Okay, you got it? Tension. What about here? As the moon orbits the Earth, what is the real identity of the centripetal force? Gravity, gravitational force. Okay, as a race car turns on a banked curve on a racing track, what is the real identity of that centripetal force? Think about it. So it's a banked curve. So what kind of forces are acting against it? Believe it or not, that's going to be a combination of your normal force with the help of static friction. The static friction keeps it from sliding off the track, and the normal force keeps it is that support force from the track, okay? As you swing a mace in a vertical circle, so vertical circle, when I'm talking about a horizontal circle, I'm talking about like something that's going to go along the horizon. A vertical circle would be more like a roller coaster type circle, okay? That's going to end up being your vertical circle. So in this case, I've got a mace that's swinging in a vertical circle. So what's acting on that? Tension and also gravity. And then that goes over here, Tennessee tornado at Dollywood. What is the real identity of the centripetal force? So right up here at the very top, okay, you're hanging upside down here. What is the identity of the force on you? Well, let's think about that. We have your weight coming down, so your mass times gravity. Is there anything else? There is. It's going to be your normal force. Okay. So, our very first circular motion question. A jet airplane is flying in a horizontal circle with a radius of 500 meters. So, we have a radius of 500 meters such that the jet will complete a full circular motion in a time of 25 seconds. Okay, so that's going to be our time. How many G's? So a G, 1 G is equal to 9.8 meters per second squared. Of radial centripetal acceleration does the pilot experience? Okay, so when we think about this, we are wondering AC equals V squared divided by R. Okay, that's our main equation. So we need to look at this and say, well, do we have any idea what our velocity is? And we don't. But let's think about a circle. Go back to your crash course video. And when we have a circle, the distance covered by a circle is called your circumference. Your circumference is 2 pi times r. Okay, so that's the full circle covered. And then that full circle is covered in 25 seconds. So your distance is 2 pi r and your time is 25 seconds. So your change in distance divided by your change in time is really 2 pi r divided by 25 seconds, or your period of time. And in circular motion, we actually use a capital T, but I used that lowercase t to kind of drive home the point. So when we look at centripetal acceleration, we're looking at 2 pi r divided by t, square that, divided by r. Okay? When we go ahead and manipulate that, we get 4 pi squared r squared divided by t squared r. So one of your r's is going to end up canceling, and you're going to end up getting 4 pi squared r divided by t squared. Okay, and that's going to end up giving me 4 pi r is going to be 500 meters. Okay, we don't want to forget the square here on the pi, divided by 25 seconds, and that's going to end up being squared. Okay, so that's going to end up giving me 31.58 meters per second squared. And we're being asked to figure out how many G's that is. So for every 1 G, I have 9.8 meters per second squared. So when you hear like a pilot can pull a certain number of G's, or in a roller coaster, you have a certain number of G's, this is what we're talking about. Meters per second cancel, and we end up getting G's in the end. And in the end, this is 3.2 G's. Okay? So looking at our next question, it says a speck of dried clay sits on the edge of a potter's wheel with a radius of 15 centimeters. So we have a radius of 15 centimeters. If the speck of clay slips off when the wheel's rotation rate reaches 75 RPM. So it slips off. So what does that mean? That means that the static friction has been overcome. Okay? Calculate the coefficient of static friction. So we're trying to calculate coefficient of static friction. So what kind of values do we use? Well, we know we have 75 revolutions per minute. That's what RPMs is, okay? And so that's going to end up converting. I'm going to convert to meters per second. Well, I know that for every 1 minute, I have 60 seconds. And I know that for every 1 revolution, I have 2 pi r. So I have 2 times pi times my radius in meters, which is 0.15 meters. Okay. Minutes cancel. Revolutions are going to cancel, and I'm going to end up getting meters in the end. I get 1.18 meters per second. Okay. And that's basically going to give me a velocity value. Okay. So it says the speck of dry clay sits at the edge of the potter's wheel with a radius of 15 centimeters if the speck slips off when the wheel's rotation rate reaches 75 revolutions per minute. Okay. So then the next thing that we want to figure out is we want to figure out our sum of forces. And remember, this is a centripetal force. So our sum of forces is equal to mass times centripetal acceleration, which is the same as mv squared over r. Okay. So what is that equivalent to? Well, my sum of forces in this case, what forces are acting on this piece of clay that's going around a potter's wheel? Well, the only force acting on it, we said that the centripetal force has an identity. And the identity in this case is our static friction. So we know that static friction is equal to our coefficient of static friction times our normal force. Okay. And we know that normal force is mass times gravity. Okay. So when I combine these two equations right here, I end up getting mv squared divided by r is equal to my coefficient of static friction times my normal force, which I know is going to be equal to mg in this case, because I don't have any angles. Okay, so mass cancels, and I end up getting that my coefficient of static friction is equal to v squared divided by r times g, because I took my g and I brought my g to the other side of my equation. So when I go ahead and plug everything in, I have my 1.18 meters per second. I square that, divided by my radius, which is 0.15 meters, times 9.8 meters per second squared. Okay? And that's going to end up giving me a value of static friction equal to 0.95. Okay? So before we go on to our next question, I want to talk to you about roller coasters, because roller coasters are going to be super important, obviously, in this class, but also just in general, roller coasters. The idea of a roller coaster really applies the stuff that we've learned. So in this case, we are using this Evel Knievel bike rider, okay? And we have the radius of our circle right here, and our bike rider comes up, loops around going upside down, and comes back around. Okay. And so what I like about this diagram is it shows you what are the sum of forces. Well, right here, down here at the very bottom, we have our normal force, which is the supporting force of the ramp, basically, or the loop, pushing up onto the bike rider. And then we have the mass times gravity of the bike rider. And when you sum those together, that's equal to your centripetal force. So your sum of these forces here is equal to your centripetal force, which is mv squared divided by r. But that sum of forces is also equal to our normal force minus mass times gravity there. Okay, so you can see that right here in this equation. Okay. Now, when you look at number 2, when you're looking at the centripetal force is just equal to the normal force pushing against the bike rider. So that's equal to mv squared divided by r. But what I like about this top value, you got to think about it. Like when you're sitting in a roller coaster, what is working with you? What do you feel? And you feel yourself being pushed into that seat, right? Because your body is resisting motion, or resisting a change in motion due to Newton's first law. So because of that, we end up having our normal force pushing down, and then we have our mass times gravity, or our weight, pushing down. So our sum of forces here, or our centripetal force, Our sum of forces there are equal to our normal force plus our mass times gravity. And all of that is equal to our centripetal force. So you can see that right here. So point number 1 and point number 3 are super important to remember. So when I look at this question, this is our last question for today. We have a child takes a ride in a roller coaster. A certain portion of the ride involves vertical loops that can be approximated as circular, each with a diameter of 18 meters. So if we have a diameter of 18 meters, that means that we have a radius of 9 meters. If the coaster passes through the loops at a rate of 25 meters per second, so that's going to be our velocity, what force does the seat exert on the child at the lowest point of the loop? Okay, so we're looking at when you come around, okay, the lowest point of the loop. At this point, remember from our last diagram, we have our normal force going up and we have our mass times gravity going down. So our sum of forces is always equal to our centripetal force whenever we're dealing with circular motion. And this is just like in our previous problems where we always wrote sum of forces equals mass times acceleration. And then separately, right, what is the identity of those forces? Well, the sum of those forces are my normal force is my positive. And the reason I set that as my positive is because it's the direction of my acceleration minus my mass times gravity, okay? So I end up taking these and putting them together. I get mv squared divided by r equals normal force minus mg. And I'm trying to solve for normal force because I'm trying to solve for the force that the seat exerts on the child. So I end up getting that my normal force is equal to mv squared divided by r plus mg. So I end up getting that we have a 40 kilogram child times 25 meters per second squared, and I'm not putting my units here for sake of space, plus or divided by 9 plus 40 times 9.8. And in the end, I end up getting that the force being applied by the seat on the child at that point is 1,032 newtons. Okay? Now, what force is exerted on the child at the highest point of the ride when the child is upside down? So at this point, I have my normal force and I have my mass times gravity. So my sum of my forces is always, again, equal to mv squared divided by r, or na. And a is v squared divided by r. My sum of my forces is also equal to my normal force plus my mass times gravity. So when I combine those two, I end up getting mv squared divided by r equals normal force plus mass times gravity. Okay? So then we figure that our normal force, or the seat of the push of the seat, okay, is equal to mv squared divided by r minus mg. So we have 40 times 25 squared divided by 9 minus 40 times 9.8. It's really important for you to realize that the sign really matters in these questions, because in this case, I get that the force by the seat is 248 newtons, okay? The next question says, what is the slowest speed at which the coaster can round the top of the curve without dropping the child out of the seat? So in a normal situation, we have, this is our free body diagram, where we have normal force pushing down and mass times gravity. But this is going to be the hardest thing for you to understand through a video. And what is important for you to understand is if somebody starts to fall out of the seat, what happens? Which of those two forces is no longer there? And if you said the normal force, then you are absolutely correct. So what ends up happening is we take our equation, our sum of forces, equals mv squared divided by r. And our sum of forces, we're at the top, so that's equal to normal force plus mass times gravity. And so we end up getting mv squared divided by r equals normal force plus mass times gravity. But here's the kicker. At this point, the minimum without dropping the child, okay? That means that my normal force has become zero. It's become non-existent at the point where the child starts to drop. So now we have mv squared divided by r equals mg. Now, I have an m here and an m there, so I'm going to cancel those. I end up getting that my minimum speed is v squared divided by r equals g. When I manipulate that, I get v is equal to the square root of r times g, which is the square root of 9 times 9.8 meters per second squared. And that is going to end up giving me a value of 9.39 meters per second. Okay, so I hope that was helpful. If not, if you need anything, then go ahead and reach out. Make sure that you